Thanks for downloading the InOurTime podcast. For more details about InOurTime and for our terms of use, please go to bbc.co.uk/Radio 4. I hope you enjoy the programme. Hello, the Nobel Prize-winning British physicist Paul Dirac declared that the laws of nature should be expressed in beautiful equations. True to his word, he is responsible for one of the most beautiful. Formulated in 1928, it describes the behaviour of electrons and is called the Dirac equation. But the Dirac equation is strange. For every question it gives two answers, one positive and one negative. From this its author concluded that for every electron there's an equal and opposite twin. He called this twin the anti-electron, and so the concept of antimatter was born. Since then, physicists have created antimatter in the laboratory, and we even use it in our hospitals, but antimatter remains fundamentally mysterious. There should be much more of it around, but there isn't, and to understand why may bring us closer to understanding events at the origin of the universe. With me to discuss antimatter are Ruth Gregory, Professor of Mathematics and Physics at the University of Durham, Frank Close, Professor of Physics at Exeter College, University of Oxford, and Val Gibson, Reader in High Energy Physics at the University of Cambridge. Val Gibson, let's establish some basic definitions. Before we talk about antimatter, can you outline us the picture of matter and explain how that breaks down?
Yes, of course. Matter is the stuff that we and everything around us is made of, right? So if you had the most powerful microscope in the world, you could look inside yourself and you would see that you're made of atoms. And in the atoms, you have a nucleus, and surrounding the nucleus is a cloud of electrons. And the nucleus is made of what we call protons and neutrons. And then if you could peer 1,000 times deeper inside the nucleus, you would discover that the protons and neutrons were made of quarks. And these are the limit of our resolution, and they're the smallest particles that we know about. And that's why, along with the electrons, we call the quarks the most fundamental particles. Now, in ordinary matter, you'll find that there's two sorts of quarks. There's up and down quarks, and each of them have a different charge. The up quark has plus 2/3 the electron charge, and the down quark has minus 1/3 the electron charge. And they just combine together, two up quarks and a down quark, to give us the proton, and two down quarks and an up quark give us the neutron. So and that's what matter is.
And that's tables and everything.
Everything you see around.
And so on and so forth. Can you give us some idea of the sizes involved here? Just start with the atom, because after that it gets to be sheer imagination as far as I'm concerned.
Yeah, I mean, the atom is of the order of what we call 1 angstrom. So it's 1 over 1 and 10 zeros meters. Right?
I'm sorry to reduce this as a nursery, please forgive me, but I read in the notes that 1 million atoms would go across one strand of hair.
Yes,
the breadth of one strand of hair.
That's
right. More to my kind of... I mean, I can't imagine that either, but it gets a bit nearer.
Yes, that's
so we're
right.
We're going to be talking about the most fundamental things in nature based on the most minute things that we know about.
Absolutely.
So this is a rather nice...
yes. Yeah.
Right, given the picture of matter, which you've been
Yes.
very clear about, down to the building blocks, the quarks, which is a wonderful word. What's antimatter?
Well, antimatter, although it's beloved of science fiction, right, it's not extraordinary in any way, right? For every matter particle, it has a partner which we call an antimatter particle. And in most respects, they're identical. If you could see it, it would look the same as matter.
But you can't see it.
But you can't see it. If it would look the same. It has the same mass. It has the same size. It has the same amount of electric charge. But in one respect, they are very different. And that is, for example, the electron with minus electric charge, the antimatter equivalent of the electron, which we call the positive electron or positron, has plus electric charge. So that's the main difference between them. There's also another subtle symmetry between them, and that is, as an electron travels through matter, it likes to spin, and it spins with a left-handed corkscrew. Whereas the positron, when it travels through matter, it spins with a right-handed corkscrew. It likes to travel right-handed. And seems to be a perfect symmetry between the two.
From my reading, antimatter is something that you find the most mysterious, and that's what we're going to get towards in this programme, the most mysterious entity or non-entity.
Well, it's mysterious in the sense that we don't know where it is, but it's not mysterious in the sense that we can... There's lots of antimatter being made all the time. For example, when high-energy cosmic rays travel through the atmosphere, it produces lots of antimatter. We can make antimatter in particle accelerators. But the mystery is why there is more matter than antimatter.
Frank Close, I mentioned in the introduction that antimatter was first conceived by Paul Dirac in what's now known as the Dirac equation. Can you explain in a little more detail what that equation is?
Well, it was back in 1928. Dirac was a mathematician working at Cambridge, and quantum mechanics had just been created. And Dirac came up with the idea of trying to combine quantum mechanics with the other great pillar of 20th century physics, which was Einstein's theory of relativity, and to apply it to the simplest thing then known, the electron. And the surprise was that he found that he couldn't do it, at least not just by writing a single equation. He set out to write a single equation to describe the energy of the electron. And the equation insisted upon splitting into 4 parts. I mean, in mathematical jargon, he had to use matrices, but for our purposes, there were 4 equations, whereas he only wanted 1. And they all had to mean something, and the question was what? Now, he quickly realised what 2 of them meant, as Val had said. The electron has a sort of corkscrew. Think of it as a spinning top going clockwise or anti-clockwise. And that spin had been recognised must exist because people knew from the way that atoms behaved that when electrons were in magnetic fields they would spin one way or the other. For the first time, Dirac's equation was saying, aha, that is why there's a doubling up, these 2 spin possibilities. But what about the other 2? And that was the great puzzle, because as he looked at the equations, they seemed to be saying the electron can exist with negative energy. Now, at this point, I imagine Dirac's thoughts were probably like the listeners. What's going on here? I mean, negative with respect to what? What on earth can this mean? And clearly it's a nonsense phrase that way. And then he had what to me was the great insight, which was there was another way of interpreting this doubling up. And it was that the negatively charged electron with negative energy, that it seemed to be saying the equations wanted, could also be read as saying a positively charged electron with positive energy. So now at least one had got something sensible. Positive energy had appeared, which makes sense. But a positively charged electron, there was no such thing. Nobody knew of any such thing. The only positively charged particle that was then known was the proton, and there's been a lot of debate about whether Dirac actually thought that he had explained the proton. The fact that it's 2,000 times heavier, he thought might just be an incidental problem to be solved later. But within 4 years, the positron was discovered in cosmic rays by Carl Anderson in the States. The way he detected these things, just like aircraft flying across the sky leave a vapour trail behind them, so charged particles passing through what was called a cloud chamber would leave a little trail of drops where they'd gone through. And with a magnetic field around the chamber, you could make the trails bend left or right depending upon whether their charge was negative or positive. So Anderson discovered a trail in his cloud chamber with all the characteristics
This
of
is in America,
Yes, in America. With all the characteristics of an electron, except it bent the wrong way, a positively charged electron. So that's 4 years after Dirac had written his equations, and to me it's remarkable. I find it in a strange way quite uncomfortable that Dirac is scribbling things on a piece of paper, and the equations say, you can't just have an electron, old boy, you've got to have a positive version as well. And the equations know about nature, and then we go out and do an experiment and discover that's how it is. It's a very profound, in some ways disturbing thing.
Ruth Gregg, what did it signify, this theory of Dirac? How did it take the argument forward?
Dirac, if you like, was one of the pioneers of taking quite a sophisticated mathematical equation and yet extracting physics from it. And it's begun a dialogue between mathematicians and physicists that continues to this day, where people trying to find out the very fundamental theories of nature, do turn to mathematics to try and get tools to help them. And also, actually, it's not just a one-way street. People working on fundamental theories of physics have come up with mathematical advances, which then the mathematicians have gone off and taken and worked out and found to have some very interesting and deep, mathematical worth as well. So I think this was, if you like, the start of a beautiful friendship, so to speak, between mathematicians and physicists, which has led to a lot of interesting new ideas.
What antimatter is, how it was arrived at, I think has been very well described. one of the big points for myself. What happens when matter and antimatter meet? Now, can you describe that graphically, please?
Graphically. Well, I think you've now got to the reason why antimatter is so beloved of science fiction writers, and of course the reason that it's used for the propulsion system of the Enterprise. So what we've found out is that matter and antimatter appear the same from afar, but once you get in closer, you see that what matter does, antimatter does the opposite. Electron spins left, positron spins right, electrons negative, positrons positive. It's as if the two are mirror images of one another, but the only thing they have in common is they both have a positive mass. So what happens when an electron and a positron meet is they completely annihilate. So they destroy each other in a burst of energy, of radiation. And so when matter and antimatter meet, the simplest way of putting it is that they totally wipe each other out. So why is this spectacular? Why do science fiction writers like this idea? Well, if you think now of a nuclear bomb, say the original Trinity test, in that explosion, only about, say, a gram of matter there is annihilated. So 1 gram of matter, or annihilation of matter in a nuclear test, is what gives you that huge mushroom cloud. So imagine what a kilogram of antimatter meeting with a kilogram of matter would do. It would be like having 1,000 nuclear bombs going off all at once. So that's pretty dramatic, if you can do it.
Well, the good news and the bad news. The good news is, do not worry about the idea of an antimatter bomb. I mean, the good news and the great paradox which is confronting us all is antimatter doesn't exist out there. You just don't dig it up. You can't dig up antimatter and make your antimatter bomb. You have to make anti-atoms one at a time. And the fastest we can do that today, even if you could do it 1,000 times faster, to make even a gram would take you as long as the universe. So that's the good news. Don't worry about antimatter bombs. Of course, the bad news is don't think very much about antimatter being a source of power. It costs you more to make it than you get back at the end.
But let's come to this question now, Frank Close. Why there isn't more antimatter in the universe? There's plenty of matter, but very little antimatter. This is an asymmetry. Can you develop that?
Well, the experiments that we've done at CERN by using positrons and annihilating them with electrons at very high energy...
Can you just remind everybody what CERN is?
CERN is the particle physics laboratory in Geneva. And for many years, at the end of the 20th century, they were able to accelerate positrons and electrons around a 27-kilometre ring to almost the speed of light, smashing them into each other head-on. And from the annihilation energy, for a brief moment in a very small region of space, you were recreating the sort of conditions that the universe itself had about a billionth of a second after the original Big Bang. And so at the individual particle level we can see what was going on then. And what we find is that particles of matter and antimatter, electrons and positrons, quarks and antiquarks, protons and antiprotons, emerge from this in perfect balance, which is what our understanding of the symmetries between matter and antimatter that were buried in Dirac's equation, and every experiment done since pretty well, says should be the case. Which is fine, up to a point. We understand in pretty good ways how the particles of matter ended up making atoms and stars and galaxies and you and me and pretty well everything we see out there today. But the antimatter, we don't find any at all pretty well in bulk.
Val Gibson, can I come back to you? What evidence is there for thinking that there was an equal amount of matter and antimatter, what is a billionth of a second after the Big Bang?
Well, if you take yourself back towards the Big Bang, you may ask yourself what was there, right? And what the common belief from the cosmology side of things is that there was just energy there. And in the same way that Ruth says when you've got matter and antimatter, you bring them together, produce energy, then you can go in the reverse process and you have energy to start with, and that will give you matter and antimatter in equal amounts. All right? So at the beginning of the universe, all that energy turns into matter and antimatter. And at that point, then the matter and antimatter can annihilate again and become energy and so on. But we found that there must be some flaw some flaw in the
Because
laws
just
of nature.
To jump in for a second here, we've been told categorically that they annihilate each other. So why didn't they annihilate each other before they got started?
Good question.
Good question.
If the temperature is high enough, so if we're in the very early universe when conditions were very different from today, in some sense we can't just say, oh, it'll all annihilate, we'll all go back to having energy. There's a lot of jostling, a lot of going one way and going the other way, and so it's where that takes you to that's
Yes,
that's
I mean,
the real question.
There's an analogy that you can do at the beginning of the universe. We've got all this matter and antimatter around, and you can consider them, if you like, as two armies, right, that meet. And if you had an army, say in the Napoleonic times, where you've got the ranks and you've got muskets and they are firing at each other, then, and the ranks, as it works, you fire, you kneel down, you reload, and so on. So you get waves which go through the matter and antimatter armies. And you just find that the matter is just slightly quicker, right? It's just slightly quicker than the antimatter army. And the net effect of that is it soon annihilates all the antimatter and you're just left with matter. And that happens in the minutest fraction of a second, which actually would give you the imbalance of matter and antimatter at the beginning of the universe.
The whole universe as we perceive it now is but 1/1000th part of an even grander creation. We're the little bit left over after that huge annihilation took place.
Oh, so you're saying that antimatter might be somewhere else?
That is one possibility. We suspect that there is something subtly different between matter and antimatter, and exactly what it is what we're trying to find out.
I mean, we're talking here about the early universe, and the biggest observation we can have is that we are made of matter and not antimatter. However, we can recreate the conditions of the early universe in the particle physics experiments that we've done, and we can recreate this matter-antimatter asymmetry in the experiments themselves. And in fact, one of the greatest breakthroughs, I think, of recent times was the discovery of the matter-antimatter asymmetry in the 1960s. And that showed us that we could explain this flaw in the symmetries of nature, right? Unfortunately, the flaw's not big enough to explain the universe completely made of matter, so there's something missing.
Is it taking this on, Ruth Gregory, to talk about the process of baryogenesis? Can you tell us what a baryon is first, and then baryogenesis, and why this fits into the process we're going through now?
Well, I mean, I suppose, just put it simplistically, baryons are the stuff, that our nuclei are made of. And so, in a sense, you could think of, when cosmologists use baryons, we're often using it as a shortcut to saying matter in the context of this discussion. And so, when we talk about baryogenesis, then we are talking about the generation of matter. It's perhaps worth pointing out that we have so many interesting questions in cosmology, but one thing we should remember is the matter that we are made of is actually a small component of the universe that we live in. There's an awful lot more out there.
Mark Gibson, just to say where you are in finding out about this vital asymmetry.
The first discovery of this asymmetry in the laboratory was in 1964, right? And that was with something called the kaon, with this very strange quark. Now, we now know from the experiments that we did at the end of the last century that we have what we call three families, three generations of quarks. We have the up and down quarks, that all matter is made of. We have the second generation, which includes this strange quark, and we have a third generation, which has what we call the top and the bottom quark. There is no other quarks around. So we've seen the matter-antimatter asymmetry with the second family of quarks, and we now know that we would expect a bigger effect in the third generation of quarks. And we indeed have done experiments at the end of the last century which have shown that we get bigger matter-antimatter asymmetries, a factor of 10 bigger than the second generation, using this bottom quark. Right? So that has now been discovered. So we've seen it two places in the laboratory. Unfortunately, both of those places, the amount of matter-antimatter asymmetry that we observe is still not enough to describe the overall matter-antimatter asymmetry in the universe. So we need some new phenomena which is going to produce a bigger effect.
So you need more evidence?
It's got to be some new physics out there. It may have a label of something like supersymmetry, extra dimensions, multi-Higgs models, you name it, right? There's
And
lots
this is
of
a terrible
theories of
anarchic
it.
thought, but it kind of reminds me of Bertrand Russell saying, if you woke up dead and met God, what would you say? And he would say, "Sir, yes, I'd call him, sir. You should have given me more evidence."
That's the solution we're looking for, right?
Ms. Gregory, can we come back up, not back, but in a slightly different direction? Can you give us any sense of the challenge involved in trying to understand the behaviour of matter at high temperatures?
Val has said that in the colliders, the conditions of the early universe are recreated.
In the CERN colliders,
yes, that's
22
true, but
kilometres
it's in a highly specialised and very small sense. I think when we study high energy physics, we often tend to take for granted these. At the very beginning, you said, "Oh, all the zeros," and I think I'm not sure whether we truly understand it or whether we just become used to it. But in the very early universe, if you wind the clock back, our universe we know is expanding now. So you wind the clock back, it contracts. So the very early universe was a very compact, small, dense and extremely hot place. So as you squash things together, they tend to heat up. And one of the things that we know about matter in general, and certainly about the theories of physics, is that as you heat things up, they tend to change in nature. So we have ice, we warm it up and get water, warm that up, it boils and we have a gas, steam. If you had someone coming from outside with no means of measuring the temperature, they may think those were three different states, three different things, three different compounds. But in the early universe, the same sort of thing happens. As you heat it up, our whole idea of physics changes. So the matter that we see and are made up of now is not necessarily the same. We wouldn't see the same things as we go up to higher temperatures. And I think the real difference between the early universe and the colliders, where we try and recreate those conditions, is the fact that it's not just at some single point under the tunnel under Geneva, but it's everywhere. And this idea of having something where everywhere is at that temperature is at least one possibility for accessing new phenomena. We believe, because we've worked very hard at trying to think about how the physics we know would behave, we believe that there isn't a way of creating this asymmetry of matter with the physics that we know. But of course, there's always the possibility of someone coming in with a brand new idea.
Can we come back to antimatter in this way, Al, that you said, I think, at the beginning, that you can create antimatter and it is in use now. Can you just tell us what those ways are?
Well, there are useful, if you like, ways that antimatter can be used, and I'll just give you one as a spin-off of all these studies, really, is that if we go back to our beloved positron, that's being used in hospitals all over the country, in PET scanners, positron emission tomography scanners. And that is a pure use of antimatter.
What does it do?
Well, a PET scanner, you have to inject the patient with a small radioisotope that emits positrons. And you can detect the positrons, for example, in the brain. When they collide with the matter in the brain, you get two photons, some light coming out, and it comes out back to back, 180 degrees apart, and you can just...
But isn't annihilation going on there, then?
Yes, that's right, yes.
So
it's not harmful. It's not harmful.
You mean you put things in your brain and it annihilates things and this is not harmful?
It's not
You've got a million of these things in there. You don't mind if you lose a few, and indeed it is.
Depends who you
remarkable.
are, really. Well, we'll let that pass.
Right,
that is one of the best uses of antimatter, but we just do it for the pure research of trying to understand what nature is, and in order to do that we can make anti-atoms at CERN. We can't contain them very well, right? We don't have huge bottles sitting in a laboratory somewhere. We have a few thousand at maximum.
Well, if they went in bottles, they'd bomb the bottles, wouldn't they?
Absolutely, yes.
Yeah.
You've got to try and keep it away from matter.
Yeah,
So
very
that's
clever
very,
confinement
very difficult.
with magnetic field.
So would you confine it
in what we call a magnetic bottle, right?
What's
So
a magnetic bottle?
A magnetic bottle.
And so there's antimatter around the place now, but it's in magnetic bottles. If we let it out, it would...
the problem is it always collides with the matter,
Yeah.
and then you lose it.
I think you mentioned the phrase pure research, though, Val. You are talking about going into this for the sake of going into it, and in a sort of way, hoping that the law of unexpected consequences kicks in.
Yeah, the thing that drives me and I hope my colleagues is we do it really just to try and understand the laws of nature. And so the biggest project is that's going to happen, going to start next year, and that's the Large Hadron Collider. Physicists, thousands of physicists across the world.
This is kilometres long.
Yeah,
Isn't it?
thousands of physicists, engineers, students all over the world have been working on this for 15 years, and it's now going to come to fruition next year. We had a 27-kilometre tunnel which we collided electrons and positrons in at the end of the last century. We've now replaced all the magnets and things in there to enable us to collide protons on protons. And that means we can go to the highest energy ever achievable in order to understand, to look for the new phenomena out there. Now, when I say the highest energy, it's not actually that high. I mean, the energies we're talking about, if you had one proton of energy, it's just like having a little elastic band and a piece of paper. You just flick it across the room. It does nothing, right? It just falls to the floor. But when you put 100,000 million protons in bunches and you accelerate them to the speed of light and you collide them together, and it's in such a small area, right, such a 1/100th of a millimetre or something area, then you've got such a concentrated energy, then all that energy you can turn through E = mc² into mass. Right? Experiments at CERN will be looking next year for new forms of mass, new forms of matter, which will hopefully give us some indication of the new phenomena around.
Is this a sense in which evidence is overtaking theory? Because Dirac had a theory. He didn't have a collider. And later this was proved to be true. So is there a sense in which you're saying that we've come to the end of theory, we've got to have some more evidence before we can construct any more theories?
No, if you go through history, you find that theory sometimes leads the way, as in the case of Dirac, writing equations which predicted things which were then found. And other occasions you have experiment leads the way. And the best example perhaps of that was the origins of quantum mechanics. It was the fact that experimental phenomena seen in the end of the Victorian era led to the invention of quantum mechanics. So sometimes it's an experimental discovery that demands an explanation that points us the way to go. And that is in part where the LHC, I think, comes in on both sides. On the one hand, there are fundamental ideas in theory which say that there are phenomena which we expect to manifest themselves under the sort of conditions that the LHC will access. For example, discovering the Higgs boson, of which you've talked about many.
Collider,
yes, the Large Hadron Collider should be able to discover the Higgs boson. But the thing that I am sure of is, only nature knows what's really going on. The answer's out there somewhere, and the LHC is the only way we know that we can go and answer such things within the technology that we currently have.
So I just want to say I hope I haven't given the impression that experiment is leading the way. I think the problem is theorists are perhaps getting too clever. We have several very good ideas about what may lie beyond. The problem is that we, as theorists, have no way of discriminating between them at the current time, and this is what we're waiting for.
Well, from tier 3 theorists, you've enlightened me massively, and I hope that I can remember it for long enough. Thank you very much, Ruth Gregory, Val Gibson and Frank Close, and thank you for listening. Next week I'll be looking at the divine right of kings in the 16th and 17th centuries.
We hope you've enjoyed this Radio 4 podcast. You can find hundreds of other programmes about history, science and philosophy at bbc.co.uk/Radio 4.